Ivy, what color weighs less than the color blue?
What?
Light blue.
That's bad. Hi everybody, we are talking about light and color today.
And our guest scientists answering today's questions are Catherine Devine, Professor of Physics at the College of Idaho, and Henry Charlier, Professor of Physics at the Boise State University.
Professor Devine, how and why does a rainbow form an arc?
Rainbows form from ice or water crystals in the air. And so what those crystals do is they act like little prisms, and the light comes through them and gets bent out. And they bend depending on the length of their wavelength, so the color of the light. And so red light gets a little bit less bent and blue light gets the most bent, and you get it spread out into a rainbow of colors. The reason it looks like an arc is because when you're out looking into the atmosphere, you're looking up kind of on the dome of the sky above you. And so you're seeing the curvature kind of the sky above you and the atmosphere, the particles in the atmosphere. And so the sunlight travels straight through it. It gets bent out into this curve because you're looking up at the sky, which appears curved to you. And then the light bends out into this nice curved rainbow.
Hi, I'm Liberty from Boise, and I was wondering, if you shine a flashlight into the sky, then will it keep going until it hits something, like even if it's in space?
Technically, yes, it could keep going. There's a good chance that your flashlight beam would hit something, though, before it even got off the planet, and that's because Earth's atmosphere is in the way. So there's a lot of dust and gas between the surface of the Earth and outer space. And so the light waves would probably get scattered out before they got to the top of Earth's atmosphere. But let's say you were able to get some of those photons or those pieces of light from your flashlight got out to space. Then technically they would keep going. One of the tricky parts, though, is that it would be, as you get further away from something in space, it gets very, very faint. That's why our sun is bright and other stars are faint. And so I'm not sure anybody from another planet would be able to actually see your flashlight, but they might get a photon or two from your flashlight.
Hi, I'm Ivy. I'm from Idaho Distance Education Academy, and my question is, does anything move faster than light?
To the best of our knowledge, no. The speed of light is kind of the cosmic speed limit, as current physics understands it. So nothing can travel through space faster than the speed of light, to the best of our knowledge.
Jacob would like to know, what is color?
So from a physics and astronomy point of view, color is very much all about the wavelength of light. And so when astronomers talk about colors in an image, for a visible image, we're definitely talking about the wavelength of the visible light. Astronomers also use what are called false color images, where we use different wavelengths, so the longer wavelengths, and we put those through a computer and assign the shortest wavelengths as blue and the longest wavelengths as red, so we can make a photograph that you may have seen, like infrared images in magazines or in newspapers. And those are interpretations assigning colors to wavelengths that your eye can't even see.
Hi, my name's McKenna, and my question is, how can our eyes see different colors?
Okay, so our eyes see different colors because we have special cells that are in our eyes, and these cells are they're set up to see certain wavelengths of light. So we have different types of cells. Some are called cone cells, and cone cells detect color. They're the things that we call color. We have some that specialize in seeing green, red, and blue. And when red gets hit, when the red cells get hit, we see red. When the blue cells get hit, we see blue. But when blue and red get hit, then we might see a different color. And so they all combine and give us the different colors that we see. Now, if we kind of dim the lights and we don't see much color, well, then we have different types of cells called rod cells. And these rod cells help us we kind of see contrast, black and white, grays, that kind of thing. And so that's the kind of cell that helps us see at night. And so that's part of how our vision works, I think, is probably the best way to say that.
You can test that at home too. If you're ever trying to see a very faint object, sometimes you'll notice that it's actually easier to see a faint object out of the corner of your eye than it is to look at it straight on. And that's because the rods are mostly located in the corner of your eye, but the cone cells are more located in the forward part. There's another fun experiment you can do at home too to prove this to yourself, and that is if you take you can have a friend bring a colored marker and hold it closer and closer and closer, and you won't be able to tell what color it is until it gets into the range of your cone cells. So you actually don't see color out here. You think you do, but you don't, and you can test that at home with a colored marker and a friend.
I'm Sarah, and I'm from CUNA. Are there types of light we cannot see?
There are colors that we cannot see. There is light that our eyes cannot really pick up on. We can't differentiate. That is kind of invisible to us. So that would be your answer. Our eyes have the ability only to see a tiny, tiny bit of what there could be possible to see. Some animals, for instance, can see many more types of color and light than a human can see. And so a lot of it has to do with just how our eyes are made. And so, yeah, there is types of light that we can't see.
That's all the time we have for this podcast. And Garrett, I'll do the bad joke next time.
You're on. Thanks for listening to our podcast. If you want to learn more about science topics, be sure to subscribe to the Science Trek podcast.
And for more information about light and color, check out the Science Trek website. You'll find it at sciencetrek.org.
Funding for Science Trek is provided by the Laura Moore Cunningham Foundation, the Idaho National Laboratory, and supporters like you. Thank you.